Let's continue our look at volumes of solids of revolution using the disk method. Our conditions are the same here in part 2. Y equals 2x, y equals 0, and x equals 3 are forming a area. And this time we're rotating around y equals 8. So still a horizontal line. And our object looks something like this. So it's the same object. So now there's even a bigger gap between everything. So we know that this intersects here at 3, 6. And I'm not even sure I can draw this object, but I'll attempt to. Like if we were to rotate it, it's going to look something like this. But now there'll be a hole in it. It's going to look maybe something like that. A rounded object. This isn't the greatest drawing, but something like this. Now, let's identify what big R and little r are first. So big R I'll do in red. Big R is from the outside of my object to my axis of rotation. So big R in this case must be 8. Little r I'll do in blue. Little r is from the part of the curve that's closest to my axis. So in this case, it's this distance in blue. Notice that that distance in blue is the entire part in red, 8, subtracting out this part which is in green, and we know this part in green is 2x. We know the part in red is 8. So little r must be the whole thing, 8 minus the part 2x. So we've identified our large axis and our large radius and our small radius, so we're ready to integrate. Our integral then will still be from 0 to 3 because this object is rotating around a horizontal line, and we're currently looking at it as horizontal circles, right? Circles that are stacked horizontally. And it'll be pi times big R squared, so 8 squared, minus little r squared, 8 minus 2x squared dx. And if we clean our integral up just a bit, we'll have the integral from 0 to 3 of 64 minus, this will be 64 minus 32x plus 4x squared dx. It up a little further, we're integrating from 0 to 3, and this will be 32x minus 4x squared dx, which isn't too bad to integrate. When we do, we end up with pi times 32x, that'll be 16x squared minus 4/3 x cubed from 0 to 3. If we plug in 3, we'll have pi times 9 times 16 is 144 minus 36, and altogether then this is 108 times pi units cubed. In example D, we're using the same objects, but this time we're making some changes. This time we're rotating around the y-axis, around a vertical line. So let's get a different picture here. So here's my y-axis. We're rotating this way. And again, our objects were made by the line y equals 2x, x equals 3, and x equals 0. This time we're going in this direction. So when we rotate it, we're going to have an object that'll look something like this. But that object is going to have a cone-like figure, in a sense, missing from the inside. So here's the y-axis. So one thing that's true is that our circles are vertical in nature. So since our circles are vertical, then we need to integrate everything in terms of y. So we will not be integrating from 0 to 3. Instead, since these two curves intersect at the point 3, 6, we will be integrating from 0 to 6. And everything will need to be in terms of y. So let's first consider what big R is. So big R, I'll do in red. It's the distance from my axis of rotation to the outer portion of my curve, and that must be 3. So big R is 3. Little r then, I'll do in blue, is the distance from my axis of rotation to this curve. Now, expressed in terms of x, this is y equals 2x, but we need to talk about this in terms of y. So if we take y equals 2x and solve it for x, we find that x equals 1/2 y. Right? So this distance from here to there is half of y. That's what little r is. We still have circles, so our setup is still the same. It's still pi, still times big R squared, so 3 squared, minus little r squared, 1/2 y squared dy. Notice that everything is in terms of y, our limits of integration and our functions. Now, when we clean this up to integrate, we'll have pi times the integral from 0 to 6 of 9 minus 1/4 y squared dy. Integrating this, we end up with pi times, and this will be 9y minus 1/12 y cubed from 0 to 6. Substituting in 6, we'll have 54 minus 6 cubed is 216. 216 divided by 12 is 18. So this will be 18 minus, substituting in 0, we'll get 0. And cleaning this up just a bit, we would end up with a volume of 36 pi units cubed. Let's consider one more. Let me pause to set this up. In this case, we've got a new axis of rotation. The axis of rotation is the line x equals 3. So if we set up our picture again, we've got a figure that's formed by y equals 2x, x equals 0, and x equals 3. And now we're actually going to rotate it around x equals 3. So when we're done, we're going to have an object that looks basically an upside down cone. And so it'll look something like this. And hopefully you can see in here we've got a bunch of vertically stacked circles. So we can think about our circles in this way. So everything will need to be in terms of y. We know from a previous problem that these intersect at 0, 6, or at 3, 6, so we will be integrating from 0 to 6. Let's find big R, which again I'll do in red. Big R in this case is from here to my axis of rotation. So we'll need to think about this just a minute. I know that this entire distance down here is 3, but that big R can't be 3 because I'm missing a part. And what I'm missing, I'll put it in green, is this part right here. Well, this part right here is 1/2 of y. Right? We know that from previous work. So big R must be 3 minus 1/2 y. And there is no little r in this case. Right? There's no hole in this object. So there's no washer, which is nice. So now I've got all the information I need to integrate. It'll be from 0 to 6 of my radius squared. So 3 minus 1/2 y squared dy. We could expand this. We could try to do this by use substitution. We could just unpack the chain rule. Go ahead and integrate this yourself and see what you get, and then unpause it to see if you did it correctly. I'm going to do this by just unpacking the chain rule. So I know when I integrate, my pi is going to come down, and I know this must have come from 3 minus 1/2 y cubed in the first place. That 3 would have dropped down, so that must have been multiplied out, so there should be a 1/3 out here. Also, by the chain rule, there should be a negative 1/2 out here, but that must have been divided out, so there should have been a negative 2 here to begin with. So this would be what I would get if and when we integrate this. I'm going to clean this up just a bit before I solve it. This is negative 2/3 times 3 minus 1/2 y cubed, and we're evaluating it from 0 to 6. We plug in 6, we end up with 3 minus 3, which is 0. So if we plug in 6, we end up with just 0 minus. Now we'll plug in 0. 3 cubed is 27, and 27 times negative 2/3 is negative 18. And finishing this off, we end up with a figure that has a volume of 18 pi units cubed. We'll do one more, and then that'll be all for example 1. And again, this stuff is so important that you have straight in your head that there'll be a lot of examples for this. So again, same setup. Only difference is here in part F, my axis happens to be the line x equals 4. So again, for me it's really helpful to set up a picture, so I'll redraw it. Here's the line, y equals 2x, x equals 3, x equals 0. My axis of rotation, though, is here at x equals 4. Which means now I've got a washer situation, because I will have an object when I'm done that looks something like this. This is not the best picture in the world, but it'll have to do. Right, it's a cylinder that has a hole in the middle of it. Probably help if these were dashed, but they're not, and not be an art guy. This is probably the best I can do. It's an object with a hole in it. So we will have a big R and a little r. Let's start with our circles are arranged vertically. So we know that our limits of integration will be 0 to 6. Let's start with big R. Again, we'll do it in red. Big R is the distance from the outside of my object to my axis of rotation. One thing to note is this whole piece is 4. but I only want this piece up here. So that means something was taken out, and that was this piece right here. And again, we know from previous work that this is 1/2 y. So big R must be 4 minus 1/2 y. Now there's also a little r in this case. We'll do that in blue. And little r is this distance right here, the distance from 3 to 4. And we know the distance from 3 to 4 is just 1. So little r is 1. We've got all our information. We're ready to set up our integral. It'll be pi times my big radius squared, 4 minus 1/2 y squared, minus little r squared, 1 squared dy. I'm going to clean this up a little bit. I'll expand everything just because I feel like it. When I expand this, this becomes 16 minus 4y plus 1/4 y squared minus 1 dy. Cleaning it up a little more, we've got the integral from 0 to 16, I'm sorry, 0 to 6, of, right this way, 1/4 y squared minus 4y plus 15 dy. When we integrate this, this becomes pi times the integral of 1/4 y squared is 1/12 y cubed minus 2 y squared cubed minus 2y squared plus 15y, and again that's from 0 to 6. Now it's time to substitute in our upper limit of integration, which is 6. So that will be, what's that? 36 divided by 2, 18, minus 72 plus 90, minus, when we substitute in 0, we get 0. So cleaning this up, we end up with a volume of 36 pi units cubed. And we'll continue to do more examples of this because the practice is important.